Hello, everyone, and a very good day, good evening, good afternoon, based on wherever you're tuning in from. I am Divya Mohan, and I'm a principal technology advocate at SUSE. And you're tuning into another episode of Rancher Live. So before we go ahead with today's session, the usual setting of ground rules is always going to be there. Basically, this is a session where we share knowledge. I'm learning as much as y'all are, and we're here to learn from each other and ask questions of each other. So the expectation is to actually be nice to one another, and like I said, there are going to be questions that are going to flow through your mind for sure. But we ask that you actually enter them on the chat section wherever you're tuning in from so that we can convey them to our presenter for today during the course of the session if it's relevant for the topic at hand, or we will reserve them for the end of the session during the Q&A part. So today is going to be a session with talking about WASM integration in the openSUSE side of things. You've had a lot of or rather not a lot of, but you've had a few folks come on in previous Ranch Live episodes and global online meetups talking about WebAssembly integration in different areas of our projects. We have a project that leverages WebAssembly as well for policies in Kubernetes, which is KubeBurden. It's also a CNCF project. But today I am really happy that we could actually get our presenter Michael from WasmEdge, CEO of Second State, but I know him as the person who works on the WasmEdge project on more than the CEO. But he's here with us today, and it's an honor to be having him here and talking about the openSUSE integration with WasmEdge while demoing some cool new capabilities of WasmEdge as well. So, Michael, hello, and
Hello,
thank you
Divya.
so much for taking our time to come on the episode and talk about the integration.
Thank you, Divya. Yeah, it's a real pleasure to be here. I have always been a fan of Susie and Rancher, so it's finally time for me to to be here and talk to the community. Thank you. Yeah.
Absolutely. And I've been a fan of the WasmEdge project for as long as we've known each other. So it's honestly a great learning experience for our viewers, I'm sure. But to start off this whole session, right, Michael, let's get started as to why was there a need for the project that's known as WasmEdge that you're behind at this
Right.
point. Yeah.
Yeah. So we started the WasmEdge project in 2019, right before the pandemic. The reason we started is it goes back to my personal history. So I got my PhD in the early 2000s, and after that, that's I was a very active member in the Java community. So I was one of the earliest employees at JBoss, which later got acquired by Red Hat, one of your competitors. And that's but it's all open source. So we did the first open source application server. At the time, Java made a very curious transition from the browser to the server. So if you're old enough, that's you would remember that Java used to be a browser technology. The purpose was to run games in the browser, so it's called applet. So you embed Java programs, into your browser. That's have some modest traction. People like it, but not significant commercial level interest, I would think. But then something happened that people start to use Java on the server side. That really made it take off. And I think right now, fast forward to today, that is what Java is known for, right? That's people don't think Java as a client-side technology anymore. It's entirely server, right? So so that experience was curious, and also the benefit Java brought is also cross-platform compatibility. At the time we did it, people say, you guys were doing Java on the server. That is entirely wrong, because the notion of write once run anywhere doesn't apply to the server, because server only have like one type of CPU. It doesn't even have ARM CPU at the time. It's just Intel x86. Why do you need to write once run anywhere, right? That's so it was I'd say we did it back then only because we didn't know better. That's but it turns out very curiously that developers do need that, because they typically develop application on Windows, but they need to deploy on Linux. That is actually cross-platform, right? So with Java, it makes it a lot easier than say write it in C++ and then recompile for each platform. This actually has great implication with WASM, as we will talk about that in a minute. So that's then fast forward. I at the time I wrote books about Java. I was a Java champion and noted by Sun Microsystem and all that stuff. Then fast forward to 2019, we see another opportunity that is strikingly similar. We see WASM is widely used in the browser to run games in the browser, right? But it has some traction, but not great traction. So the idea, is it possible to use it on the server as well? Because things has changed a lot since the Java days. We now have different programming language. We have Go, we have Rust, we have those type of programming languages, not the JVM languages anymore. So can we use those? Do we need a new server-side virtual machine or sandbox for those new programming languages? Of course, there are containers at the time. So so if you have Go application or Rust application, just compile to native and then a specific operating system and run it in the container. You can do that. But the container drags along the entire operating system libraries. So if you look at container libraries, images, it's like 100 megabytes to begin with, right? If you look at some of the use cases we're going to talk about, like the PyTorch library container image, that's 5 gigabytes. The smallest one is 5 gigabytes, right? That's so it does drag along a lot of things that are we feel maybe unnecessary, and also impedes upon portability, because one of the things that container goes backwards is that it's no longer CPU agnostic. You need a different container image for ARM and for Intel. If you consider the amount of GPUs or AI accelerators that are available out there, the combination exploded. That's so you would have hundreds of different combination of images you have to maintain, each for say different GPU versions or different GPU driver versions, like CUDA 11, CUDA 12 need different container images, right? So time we thought, can we have something that is truly cross-platform and also lightweight, to solve to be the new, I would say, 20 years later, we want to do the new Java. We don't want to do the old Java anymore, but we want to do something that is more aligned with the new challenges of computing, right? So then another thing that happened in 2019 is that it was at the time from 2016 to 2018, there was an explosion of blockchain technologies, and so there's lots of people are talking about running code on the blockchain. And in order to do that, you need super efficient virtual machines to isolate, because on the blockchain, all the code are potentially hostile. So you really need some kind of isolation format. And the traditional container does not fit that bill, because you can't say a smart contract is only 20 lines of code, and in the span of 5 to 6 seconds, the blockchain needs to run 2,000, 3,000 of them. You can't possibly start 2,000, 3,000 Docker containers, or Linux containers just to run those functions, right? So in the blockchain space, there has been a lot of talk about adopting WASM, and at the time we thought that is a server-side use case. That's definitely outside the browser. So maybe the time has come for WASM to be ready on the server side. So that's where when we started the WasmEdge project, we want a WASM runtime that very specifically designed for outside of the browser use case, and it's very specifically optimized for for the server or the regular computer use cases. And the project is called WasmEdge, and the project itself is written in C++, because we want it to be close to device drivers. So like I talked about, the compatibility with GPUs, with all the edge devices like Raspberry Pi, the NVIDIA Jetson device, and all that stuff. So so that's the original idea of the back in 2019 when we started the project, right? So looking back, I still think this idea makes sense, but perhaps it's a little too earlier. That's we are because immediately after that, a significant event happened, which is a pandemic. And so from 2020 to 2023, you essentially have very limited opportunity to really talk to people or to advocate for this, and it didn't also really help. That's the name WebAssembly is a misnomer because the way we want to use it. Yeah, so I'm sure you've heard it. So I noticed you call it WASM, which I like it a lot because WASM does not say WebAssembly because WebAssembly, because it's not web and not assembly, right? So it's it is a new technology for the server. So we look for use cases for that, and we have identified some and some really interesting use cases. For instance, we're going to talk about in a minute, including our integration with SUSE. That is mostly in the Kubernetes space because another thing happened is 2020 we donated the project to CNCF because we want more open source exposure, and CNCF also thought it's important to have a runtime that is not Linux, right? So it's so there's mutual interest. So we donated the project. So the project doesn't belong to any single company. It's belong to the CNCF and Linux Foundation. So we are all contributors, right? So it's so that's the use case that CNCF brought to us is really as a perhaps a lightweight alternative to containers. So what does that mean? That means if you look at today's Kubernetes cluster, when you run microservices on it, I think studies have shown maybe 60%, 40 to 50% of the CPU cycle is spent on the overhead. Overhead meaning orchestrating the containers, startup containers. If you look at Kubernetes, anything requires a container. If you want to sleep for a couple of seconds, you need a sleep container. You need to wait, and you need to start a container to wait, right? For us, that is cool, but that is it's kind of waste of resources. And if you look at other use cases, for instance, AWS Lambda, the serverless function is based on VM and containers, which to us, it doesn't really make sense because a lot of those serverless functions are transit in nature. You need to start it, run it for a couple of milliseconds, and then shut it down, right? So to have a container that has cold start time measured in, I think, 100 milliseconds, it's a non-starter. And perhaps even closer use case, if you look at GitHub Actions, right? So GitHub Actions, it's start a VM or for you to build and test, which is all fine. But a lot of people also use GitHub Actions as a bot. So, I can write a GitHub Action script to do a PR review or something like that. But do I really need or send a notification email to someone when someone submit a PR in my repository, right? Do I really need to strap out the VM just to send out that email? That's so it's so for those use cases, we thought if people like microservices, maybe they're looking for something that is lighter. That's and for that we spend a lot of time integrating with Kubernetes. And the way it works is that we try to make WASM the first class citizen in the Kubernetes ecosystem, meaning that the Kubernetes runtime. So Kubernetes has different layers of runtime. So I believe in the SUSE ecosystem you have Rancher and Kubernetes itself at the top, and it manage and then you have developer tools like Podman and things like that, and underneath it you use cryo or containerd, and then underneath that you use CRUN, right? Or sometimes use runC. So you have different layers of runtime that you load up the image from the from the image repository, and then start the image, and then shut down. Manage the whole lifecycle. That's the whole thing about Kubernetes, right? So with WASM, we want to put WASM files into the repository, into Docker Hub, or into the image repository. But instead of saying it's a x86 image or it's an ARM image, we call it the WASM image. Okay, so it's a new label. We call it WASM image. When the Kubernetes controller sees that it needs to load and run this image, it goes to the hub and download that image to the node, it would recognize that this is not a Linux image. It doesn't run on the CPU. It runs on something called WASM. And then, so instead of going through the process of starting a Linux container, it will go through alternative route to use a WASM runtime to run this WASM application. And then, after it's, so it could be a long-running application. We can show you the WASM application can also be a long-running. It can be a web server, in fact. And but it could also be a very transit application in nature. That's it's just do something and immediately shut down, right? That allows us to, in the same Kubernetes cluster with the same hub, that we would be able to run WASM services side by side with Linux container services. I think that's the key point of our collaboration with all the Kubernetes distributions and Linux distributions, even like SUSE, right? Is to make this process seamless and easy, so that people just needs to point their configure file to this WASM file that's in the OCI repository, and that's it, right? So they don't have to make special arrangements to have special shims. That's to say, to tell the although underneath it, it's probably done by the shims, or in the case of CRUN, which I believe openSUSE use, it's there's actually a conditional logic that's embedded in the CRUN code to test if the platform is WASI or not. If it's WASI, it's WASM WASI or not. If it's WASM, then it's used the WASM runtime, right? So that's yeah. So the net effect really is that it allows us to go on and build those microservices that runs on first class Kubernetes clusters like Rancher and SUSE, right? So that's so I don't know if I'm going too long or not detailed enough, what have you, but that's yeah.
I think that was a pretty great introduction, albeit a long one, but it was actually a pretty great one, given the history that you've covered, and given the actual, genesis of the interest around WasmEdge, or around building the WasmEdge project, really. And I think one of those things that we've been constantly asked, right? Even when I'm speaking to people at conference or outside of it, one of the questions that I'm asked is, why would you want to run um, WASM as a microservice? Like, why would you want to do that? Why would actually, I think it is one of the questions that we've received on our YouTube channel as well. Why would you want to run it as a microservice? Why can't you just run a WASM module as is on a runtime somewhere? Because it essentially is adding that extra layer of complexity, right? Like, again, um, there are use cases for both. Like, there were use cases for VMs, there were use cases for uh, you know uh, physically hosted servers. There still is, physically hosted servers. Cloud is someone's server at every point in time, but essentially, we get asked this question a lot. So what's your take on this? Like, do you also believe that both of these have use cases, and if so, have you seen some of these use cases live, and could you shed some light on that?
Yes, absolutely. Let me share my screen so that I can show you some of the repositories. That's
Yeah, absolutely.
which I thought it may be. I think it's this one. Okay, yeah. All right. So well, so
You might need to make it a little bigger, because the zoom in a little bit so that you can, yeah.
like this.
Cool.
Okay.
Yeah.
All right. Yeah. So this is under the second state repository because those are mostly customer examples. That's so it is based on WasmEdge, right? So if you look at those pinned examples, there are perhaps the mostly widely used is this microservice Rust MySQL. It's if you are familiar with coming from the old world of Java, this is a pet store example. So basically you have a application that does some transactional processing, but it has a web front end and it has a database backend. The entire thing is implemented in WASM. Okay, so you can see that. Let me see. There's, you can go through this project, and there's, there's a source directory, which is what we call the middleware application. It's the middleware application only has one .main.js. It starts up a server, and then it has a data structure. It writes. It assumes there's a MySQL database running somewhere, so it writes to that database. And then there's a client folder which has HTML pages that interact with the server, right? So to going back to your question, can this be done as a standalone, server that runs on my computer? Yes, it definitely can. But that's in fact, a lot of people use that this way. But in that use case, I think it's more of a developer or more of a amateur use cases, right? Where I just want to start a personal server, and let me go back to the README. Yeah, so that's to showcase that I can stand up a multi-concurrency web server in WASM, and then to have it connected to a MySQL database and have a pretty good performance out of it, right? So that's a good demonstration. But in order to really use it, I think in today's environment, this application would be considered part of a microservice, right? So meaning that the database would be deployed somewhere else, and this application takes some kind of data from the front end, transform it to JSON, and then save it to the database, and then have another request to retrieve that database, to retrieve this record from database and turn that into JSON and return that to the JavaScript. This whole thing, I think, it's in modern applications, it has to be run together with many other applications. So there would be applications that does, say, order fulfillment if this is an e-commerce, right? So it is set up to be an e-commerce application, and there's things that maybe workflow management and all that stuff. So this piece to take the input, transform to JSON, and handle the database is actually one part of the story, or even a small piece of the story. So I think it would be very natural to run it as a microservice in a cluster of services, right? So, and why in this case using WASM is the best choice? Because this whole web server plus middleware plus database connectors, everything compiled together, is under 1 megabyte. Okay, so so in your Kubernetes cluster, you could have this microservice that is truly micro, because if you are not if you use the same code just written in Rust and compile it to, say, Linux, and then try to wrap it around in a Linux container in a portable fashion, not those very slim containers that are not portable, right? But in a fairly portable Linux containers. And then you try to deploy it on Kubernetes, like I said before, it would be, you are looking at 200 megabytes, 300 megabytes at least. So we are talking about 1 megabyte. That dramatically reduces the overhead of running this as a microservice. I think the advantage is much less pronounced if you are running it on a standalone server on your own. Say I have a home server, I run it on my home server, because the typical home server doesn't need that type of density. You only need to run a couple of applications. So each application is 100 megabytes. So what? Because I have gigabytes of hardware space and memory space, right? But in a microservice environment where you are constrained by the compute density, you have a lot of microservices that you have to orchestrate together. I think to have WASM integrated into Kubernetes would be a crucial step. To give you an example, one of the I wouldn't say whom, because I guess it's controversial. It's confidential. So one of the large internet companies that we engage with, the company was started in around 2010. So so they brought full well into the microservices architecture. Within that company, there are 50,000 microservices. I'm not talking about 50,000 machines. It's 50,000 different pieces of software, each maintained by a small team. Okay, so they have 100,000 people, maintaining those microservices. And as you can imagine, when you deploy those microservices, it becomes a huge headache because each of those 50,000, each of those services would require certain amount of resources and all that. So a new dedicated framework has to be developed to at deploy time to combine some of those services into one container, because you can't afford to have each service have its own container, right? So that's so to have commonly used or services, the services that commonly occur together, they are bundled into a single container, by the ops people, and then deployed onto Kubernetes, right? So there's lots of practical considerations that people would have to do in order to make this type of application run well. And I believe WASM itself, that's by providing a very lightweight alternative to the traditional microservices would fit well. And I think this is sort of the conventional way, that's the conventional wisdom at the moment as well. So if we come to here and look at some other projects here, you would see the WasmEdge container examples where there's a bunch of microservices. They're mostly web servers or transactional processors that was configured for different Kubernetes setups, right? That's so you can, if you come here, you can see, there's different combinations: Kubernetes with containerd, Kubernetes with Llama to run large language model, Kubernetes with cryo itself, containerd without Kubernetes. That's all kinds of combinations. And there's also a WasmEdge QuickJS repository where it allows people to write applications, not necessarily in Rust or Go compile languages, but in JavaScript as well. So it supports a large set of the Node.js API and also the JavaScript fetch API, so where you can do networking application in those WasmEdge based microservices. Yeah, so that's sorry, this is a long answer, but but I want to be comprehensive here. Yeah, so.
So one of the things I think when we last caught up over email, you were saying that you were upstreaming a PR for providing GPU access to WasmEdge running under crun. Is that PR merged right now? What is the status? And can you shed a little more light on that?
Yes, so that's a excellent question. So the background of this is what I mentioned. That's we want WASM not just to be cross CPU like Java did before, but cross GPU as well. So the idea really is that in WASM you provide an abstraction layer for developers. So developers write against API called WasmEdge. It's a WASM WebAssembly system interface for neural network. It's a long name, but it's an API that's available in Rust and JavaScript. So you write toward that API, and you compile to WASM, and that's it. That's you deploy it. The machine that actually runs this thing would figure out what's the underlying GPU. Is it running on a Mac with Metal, or is it running on Linux with CUDA? And it would handle those function calls properly using the underlying GPU driver. So that allows it, for developers, because developers today all use Mac to develop their software. But on the server side, there's very few Macs. So if I have a large language model application I develop on my machine, it runs well. How do I move it to a Linux server running on SUSE and have NVIDIA in it? It's typically, if I don't have WASM, I would have to rewrite the code because it's the Metal framework versus CUDA framework, right? And not only rewrite, but also recompile, retest. And that's something Kubernetes doesn't do for you, because Kubernetes is set up to orchestrate binary artifacts, right? So it doesn't take source code and compile it on the node and then deploy it for you. You just simply don't do that, So, so in order for WASM to integrate, so in this set of GPU-rich environments, for WASM to integrate well with Kubernetes, we need for this type of applications to run on Kubernetes, we need. I think there is a strong demand for WASM. At least this is what we see in the past year. Aside from microservices, there's a huge demand for running AI workloads that compile to WASM, right? But in order for this to happen, we need to have tooling on the ups, in the C-ROM and also up,
Exactly.
from C-ROM to container D and all that, to be able to handle those drivers, because traditionally it also notoriously difficult for NVIDIA driver to work in Kubernetes environments. You have to have the container image has to have the exact same driver as the shim that installed on the node. If one has CUDA 11, other one has CUDA 12, you are baked. You are not going to be able to make it work. So there are lots of things that also to have the GPU available from the virtualized environment is also something that's I think so far it's a struggle. So there are several different ways to solve this problem. So for instance, we had a collaboration with Docker. The Docker way to do it is really to use the web GPU standard. So have another abstraction, which I don't think is that interesting to discuss it here. But with the C-ROM community, which is upstream of SUSE, is to add additional hooks in the C-ROM runtime, so that the application running inside C-ROM, meaning the WASM application, would be able to see the GPU. And once we can see the GPU, we would be able to call it. So we now have a demo. Like I show you. In my in the second state repository. There's a container D Llama demo where you can install C-ROM underneath container D and then have it load a Llama 3 large language model, and then stand up a web server. Also, everything is using WASM. Everything is written in Rust, and they only compile to WASM. It doesn't compile to any, any of the native formats. And so you would from outside, you would see your Kubernetes cluster started a web server where you can load up a chat UI and then start to chat with it. So that's so the PR has been merged. That's we are looking forward to having more examples. That's as it's become available in regular Linux distributions like openSUSE. Yeah. So.
Do we have a demo by any chance? I believe you were saying something about a demo before. So, do you want to showcase some stuff?
Yes. Let me do that.
Yep.
Well, let me.
You'll need to share the window, I guess, all over again.
Yes. Let's see that. Here, I think. Okay. All right. So the demo itself is called WasmEdge. So why do we call it WasmEdge? Is because the WasmEdge provided a runtime, but we also need the AI inference source code and all that, to build a WASM application. So WasmEdge is really the WASM application that was built. As we also mentioned, it's cross-platform. So we actually have something that's very simple. That's actually, let me cheat a little. So that's so I can just copy and paste those commands. Those commands are all in our GitHub repository, so you'll be able to see it. So you can see, I download the bash script, and then I could just do that, and it would just run everything, stand up a server. That you would be able to see. But here I use the interactive mode so that you can see what it actually does, right? So if I say interactive, so the bash script come on and say, I need to do X, Y, Z. Do you agree? Yes, I agree. So it says, do you want to install the WasmEdge with large language model plugin, which means the GPU access and all that? This whole thing is about 20 megabytes. Okay, so the whole runtime plus all the GPU drivers and all that is 20 megabytes. Consider that with PyTorch. If you are running this model in PyTorch, it's gonna be 5 gigabytes to begin with, right? That's not including the model, right? That's but since I already have it, so I will skip the installation step. Now it asks me, which model you want to run in this application. We have like 15. That's we saw that popular, but in fact, you can have any Hugging Face model that's running here, because because our the application, the way we write the application is that it takes the Hugging Face model and then send it to the runtime, either PyTorch or llama.cpp. That's or GGML. So on PyTorch, even with Llama 2 and Llama 3, there's over 10,000 fine-tuned models that's available on PyTorch. Sorry, on Hugging Face, right? So you can choose any of those and just paste the URL here. But in this case, we want to do a quick demo that says that does the Llama 3. So I would say 3 you can see corresponding to the Llama 3 8B model. This model is about 5 gigabytes. So it's the full size movie. I don't want to download it right here because if I download right here, it's going to crash this webinar. So I have done workshops where I stupidly ask people to say, run this command and download this model, and then it crashes the whole conference Wi-Fi, because it's just it's huge. So I cheated again here. I downloaded this model already and put it in this directory. So the script detects that and say you already have it. Now I can do 2 things. One is I can start an API server. That's by the way, the entire thing, including this command line. This command line is written in Bash, right? But now I want to download API server that actually runs this model. This API server is written in Rust and compiled to Wasm, right? So it says I already have it, so I don't download it. Then I start it. Okay. So what it does is that this API server loads that model into memory, and then it start a socket to listen for incoming HTTP request. So it says API is listening here. So I would just open this link, and I would come to the talk and change my screen sharing to the other tab. So
Yep.
let me see. Yeah, this chat. Okay. See, I know you probably can't see the address bar, but the address bar is localhost 8080. So this thing is entirely running on this machine, on this computer. Okay. So if I'm doing a live demo here, I would have turned off Wi-Fi here just to show you that I'm not cheating. That's none of this come from the internet. It's everything runs on this lowly MacBook machine that I bought, several years ago. And when I bought this machine, people say, "How much memory do you want?" I said, "I would just want the smallest because I only do web browsing on this machine." How wrong I was, right? Because now we use this machine to run large language model, but I want to show you it still runs, right? So if I say, let's ask some simple questions. Say, where is the capital of Japan? Okay, so the first question is so this goes to a local server that's running on my machine and use the large language model to answer this question. Okay, the first question answer is always slow because it needs to load this 5 gigabytes large language model into memory so that it can answer it, right? But you can see it's already come back. So I ask a follow-up question. What about, say, France? You see it's come back much faster, right? The capital of France is Paris. Notice this follows the conversation, so because I said, what is the capital of Japan? It's a fully formed question. But the second question, what about France? Without context, you would not know what I'm asking. What about France? Is that, about the cheese or the country, whatever, the culture or whatever. It's only because you have the first 2 questions that that I'm asking about the capital of France, right? So it says Paris, right? So let's ask a longer one. Plan me a 2-day trip to Paris. So what it does is that the machine would it does it beautifully. That's this is all local, and it's it doesn't go to the internet to search on any of this. The large language model, although it's one of the smallest large language model, it has all this human knowledge that condensed into it, so that it spits out in great logic about all those things, day 1 and day 2. And then you can see it actually, even on this Mac machine, it actually runs fast enough that is faster than I can talk, right? So if it's streaming out, I'm just trying to talk about it. It would be I wouldn't be able to follow, right? So this is the example that to show you, that's this. There's a WasM application that is both serves as a web server with a bunch of HTML, and also have not have a database on the back end, but have a large language model on the database on the back end. So it's similar to the example I've just shown you, the microservices MySQL Rust example, except there you have a web server on the front end, and then you have database on the back end. This you have a large language model on the back end. So I'm gonna switch back to my terminal to show you what's in there. So let me go here.
While you're switching this back, I'm just curious. Now, because of the upstreaming of the PR, is it possible to run these on, Kubernetes distributions, the things that you just showed? Is that what y'all were aiming for with that?
Yes. So it's so I will show you an example that's so the Kubernetes example is much harder to demo on a local machine, as you know, right? Because because by running this large language model on my local machine, I'm straining all my memory resources, because it needs to load everything into the memory and all that. Kubernetes is a memory hog. So if I do that, then I wouldn't be able to start the model. That's yeah. But the idea is definitely you can do that with Kubernetes, because you could have separate machine that has a media on it, right? So if I this is a log. It prints out a whole bunch of logs. It tells you, that's what's the raw data that's sent in there. So it goes about 20 tokens per second. Meaning if I speak like that, it's like 5 tokens per second. Okay, so 20 tokens per second is a lot faster than I can speak. It's what's more the other interesting thing about it is not only have a web UI, it also has a web service UI, meaning it takes the OpenAI formatted input. So as you know, there are a lot of tools built around the OpenAI ecosystem. Use GPT-4 as a backend. Now you can use this as a backend. That's just to send it. Just go to the tool that you use that has the OpenAI URL in it, and delete that URL and replace it with the Llama IH URL that you just started. It would function without any API keys or spending any money. So it would be a great, I would say, local LLM replacement for things like OpenAI, right? So if I exit out of it and see what's actually in this directory. So in this directory, we have the, let me show you, the large language model, which is by far is huge. It's about 5.7 gigabytes. And we have, this is the whole application. So this is the API server application. This one is 8 megabytes. Okay, so the compiled application with all the debug symbols, we have not really optimized for size, is 8 megabytes, and it's cross-platform. So there's I can just SCP or put this WASM file on a USB drive and put it on another machine that runs NVIDIA, and it would run the same thing all over again. It would be exactly the same. So that's really bodes well with Kubernetes, because Kubernetes only need to move this file around. This needs, so it needs to move it to different nodes and things like that. So I think that's the really the strength of our Kubernetes integration with openSUSE, right? That's is the portability of this thing. So people ask, that's okay. The thing you just shown, it's kind of interesting, but why? That's because there's other alternative out there. For instance, there's Olama, there's a bunch of other things, that's that can stand up the same local API server for a large language model. Why do we need something that is WASM based? So the answer is still it's the size. Size matters. That's we're much smaller. The application is only 8 megabytes and it's portable. And the runtime is like 20 megabytes or less, right? That's the way that's because the way it is so small and so it can be installed in this way, it does not require things like the pseudo privilege. It does not start a daemon. So that allows this to be embedded into other applications as well. So so if you have a application that uses this type of API server, you can put this API server into your application instead of having separate instructions to say, oh, by the way, if you want to run it on your own machine, you would have to go to download this piece of software, install it, and then start it, and then copy the URL, and then and then configure it on my side, right? You can have everything included in a single installer, right? So that would be one aspect of it. The second aspect of it really is that this API server is just something that we write. Let me show you the code that we have for it. So let me go to my the WasmEdge tab. Okay, so let me share. WasmEdge. Okay. So the entire source code of this application is in this repository. It's called WasmEdge/WasmEdge, and it's API server, so you can see it's written in Rust. And let me see this API server source, and so it does have a little more files than the one that we have shown, but most of this code is actually just handling command line options, because there's so many command line options you can pass to the LM, like the temperature, how many tokens you want to generate, how you want to generate it, and all that stuff, right? Lots of logging and things like that. But that's that's the whole thing. That's with size this big. That's that's the entire application. You can now write your own LLM applications in Rust instead of in Python. So we have a very strong notion of you do experiment with your large language model in Python to see which algorithm works and things like that. But when it comes to deployment time, you have all those encoded in a vector database and in a large language model itself. They should use a much more efficient language like Rust to build and deploy this application. It's a difference between several megabytes to several gigabytes, right? That's because the Python has so much dependency. So that's perhaps some of the values that we bring to the table, and that's also, I think, bodes well with the Kubernetes use case, because it makes it super easy and super fast for Kubernetes to copy those portable applications, portable runtimes into a new node, provision a new node, and then have application immediately start on the new node, and then have it available as a lightweight service, right? So yeah, that's well, I can go on for forever, but I'll stop here, to see if there's if there's questions, and that's.
Not at this point. All the questions that were there, I asked you. So I think that's pretty much it. Any links or anything that you want to share, please share with me, or on the side, to all the repos and to every resource that you've mentioned during the session. I will make sure that they are on the YouTube description and in a comment on LinkedIn and Twitter after the live session ends. But I think that's pretty much it for today. Michael, thank you so much once again for coming and sharing your expertise on the openSUSE and WasmEdge integration. It's been a pleasure having you, and I hope to see you at I guess the next openSUSE event that we're both going to be at, which is probably either OSS Summit or KubeCon.
All right, thank you so much. Yeah, it's really a pleasure to be here and talk with you again. Thank you. Yeah.
And thank you to all of our audience as well for tuning in today. I hope you all found this informative. See you on another live stream shortly. And have a good day wherever you are. Bye.
Bye-bye. Yeah.